We are now experts at calculating the pH of buffers, no matter what the concentration and combination of acid and base is. Now let's see how these buffers hold up to addition of acids and bases, as in particular strong acids and bases. That's the point, right? So here I want to know how a buffer that has a 1-to-1 relationship or ratio of conjugate base to acid holds up to just 0.01 molar solution of sodium hydroxide. And so just to put this into perspective, the pH of a 0.010 moles of base that is in 1 liter of solution, okay, would have a pH of 2.0. So that would be a pretty low pH for just a little bit of a base, and that's because it's a strong base. So you really have a 1.0 times 10 to the minus 2 concentration of hydroxide, right? And so that's how you calculate that. Now this buffer, we already know the pH is going to be equal to the pKa, because it's a 1-to-1 relationship of conjugate base over acid. And just as a reminder, this is the buffer that we originally calculated the pH of in the very first lecture. And just because you probably love ice tables, I have it here again. But in bold is how I would simply calculate that. Acetic acid has a pKa of 4.75, and so the base over acid concentration is the same. Therefore, we get a log of 1, which is 0, and so the pH is equal to the pKa. So, so we are, instead of having a 0.01 mole or molar solution of sodium hydroxide, we're adding 0.01 moles of sodium hydroxide to this buffer. And since it's a liter, we don't have to worry about moles and volume here. We are just looking at the mole-to-mole ratio. So we can use the pH equals the pKa plus the log of the acetate. And I was afraid I would do this. This is the way I like to write acetate. It's the same as C2H3O2. If you've had me before, you've probably seen me write. It's just a formula written differently over H. Might want to be consistent here. CH3CO2 acid concentration. Now what you have to understand is that every single mole, every single molecule of this 0.1 molar solution is going to react with the acid. So if the acid is 0.100 m in 1 liter, that means we have 0.100 moles of acid. And we have 0.100 moles of base. And that's the conjugate base, and that's important because we have all of the bases going to react. So you subtract 0.010 from the acid, you end up with 0.090 moles of acid. So we now have the pH that's equal to 4.74, which is the pKa, plus a log of 0.090 moles. But by the same token, the 0.01 moles of the acid that reacted produced conjugate base. So we are seeing an increase. So we're going to see plus 0.0100 moles. So this is going to be 0.110 moles of acid. And from that we can get the pH, and the pH is going to be 4.83. So, all right, so I told you wrong. The pH, obviously, of a strong base is not going to be acidic, like I said. 2 can't be. That's an acidic, a very, very acidic solution. But what I did is I took the negative log of the hydroxide concentration, not paying attention. So I lost some valuable points in the exam for not paying attention. Okay, so that's actually really simple, and you can still sort of use an ice table to determine that. If you set up the reaction of the strong base, and there's no equilibrium here, right? Every single molecule reacts with the acid to form the conjugate base, which reduces your acid, your weak acid, by the exact amount of base added, and increases the amount of conjugate base by that same amount. So this goes up by 0.01 moles. Okay, so there's your ratio. And then I would just use the Henderson-Hasselbalch equation, make adjustments to the volumes, the moles, that ratio, and calculate the pH that way. Anyway, that's quite a difference if you think about it, right? So you have this buffer and you're adding a little bit of base to it. If you were to add that to just water, it's going to shoot up that pH and make it very, very basic. But this buffer here, and it's very small, it's just 0.1 moles of each, keeps that right around 4.8. It's definitely still acidic, so it's working. It's working very well. Obviously, you can also use an ice table. You can use an ice table for just about anything. You can probably use an ice table to calculate how much gasoline you have to get to drive to Little Rock. I shouldn't say Little Rock. I should say Amherst, right? Okay. All right, 18 years in Arkansas will do that to you. All right, so let's have some more fun with buffer resistance. We're going to use that same buffer from the 17.3 problem here. So, and we're going to add 0.015 moles of sodium hydroxide. And so that's the same thing. We just do the pH equals to the pKa plus the log. And so instead of 0.01, we are now going to add 0.015 moles or to the 0.1, so we get the conjugate base is going to increase by that, right? So we're going to get 0.115 moles of base. The acid's going to decrease, so that's going to be 0.085 moles of HA, and we get a pH of 4.87. Now, here we are given 10 milliliters of 0.100 MHCl. Now that's an acid, first of all, so the acid's going to increase the amount of acid formed, and decrease is going to react with the conjugate base, so it's going to deplete that by exactly this amount. So step number 1 is we're going to calculate how many moles. 0.010 liters times 1.00 moles per liter is going to give me, of course, 0.010 moles of HCl. This is sort of important because we're adding it to a liter. So that increases our total volume to 1.010 liters. But the number of moles still stays the same, right? So that mole, we don't have to convert to molarity. We just need to use the number of moles. So we can still say that the pH equals to the pKa, which is 4.74 provided, plus the log. And of course now we have to subtract from the conjugate base. So we have 0.090 moles of A minus, and we see an increase in the acetic acid, so we're adding that. So here we have 0.110 moles of acid. And so that's the exact same ratio. If we were to convert this now to molarity, we would divide the number of moles by the new volume, but we would do that for the volume is the same for the mixture, so it's not going to throw us off or change that mole to mole ratio. It's not, and so we get a pH of 4.66. So we do obviously expect that pH to drop because we're adding an acid, which will make that solution more acidic. So here I have this worked out. Now here I actually converted these numbers to molarity just to show you that you have the same ratio here. You still get a pH of 4.66 whether you use the mole-to-mole ratio or the molarity-to-molarity ratio. So in this case it really isn't a big deal. Okay, let's work one more and then stop. Use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution that's 0.5 m in ammonia and 0.2 m in ammonium chloride. Okay, so now this is a base. So if we are going to use the pH equals the pKa plus conjugate base over acid, we need to take the pKb and figure out what the pKa is, and then make sure that we get the base acid concentrations correctly. You could actually also use the pOH, because that's that same relationship. The pOH equals the pKb plus, and of course I should put the log here, that's really important, plus the log, and instead of conjugate base over acid, it is actually conjugate acid, which in this case would be the NH4 plus solution over the conjugate base. So that works as well. So let's do that real quick. And so the pKb would then be 4.75 as provided, plus the log, and so here is 0.2 of the conjugate acid, 0.20 divided by 0.50, and I get an answer of 4.35. That would be the pOH, and so if I wanted to know what the pH is, then I still have to do 14 minus 4.35, and that would be equal to 9.65, which we expect the pH to be larger than 7, obviously. But I can do the same thing here, except now I have to calculate the pKa, and so that's easily done by taking the pH plus the pKa equals the pOH, 0.25. All right, so 14 minus 4.75 equals 9.25. That's your pKa, and then plus the log, and the conjugate base would then be 0.5. All right, so this is reversed. This is the base over acid, 0.50 divided by 0.20, and you get an answer of 9.65. No problem, right? Here is this problem worked out. It shows you how to calculate the pKa from the pKb, and this is the Henderson-Hasselbalch equation, base over acid. Notice that they're more careful there. They don't say conjugate base. In this case, they're just plugging in base. That ratio is the same, and so you get a pH of 9.65. Or if you prefer, you can do what I did there in the beginning. You use the pOH equals the pKb, which is provided, plus the conjugate acid-base ratio. That to me is a little bit more straightforward, but the calculation, the results are the same. All right, almost done with buffers. Not really. We're going to have a few more. So, and then titrations, and then solubility products. So, oh well.